Hi, this is a quick summary and review of what we've learned in our Physics 30S course in the first unit, which is about scientific methods. Essentially, we were learning how to do science. So how did we start our course? Well, I had a pendulum going back and forth, and I asked you, what could you observe? And you gave me a whole list of things. For example, it went back and forth, you said, and we listed a bunch of stuff. And then eventually we said, what could we measure? And when we said what we could measure, and how we would measure it. So you came up with some suggestions, and eventually we got to the question about, what could we measure that has relationships? How does, and I think we need to switch this, how does the dependent variable depend on the independent variable? So just a reminder about the independent variable is the one that we can choose the values. And the dependent variable changes as a result, okay, or what we end up measuring. And so I think we had three relationships. I think these are the ones that we decided in class. We said the period, how long it takes for the back and forth versus the angle was one of them. The period versus the weight, so you change the weight around. And the last one was the period versus the length. And so we learned how to collect the data, and the big thing we learned afterwards is different ways to display the relationships. So let's say, let's take period versus angle. We actually found that there was no relationship here. Period versus weight, we found that there was no relationship. And the last one, period versus length, we found there was an interesting relationship where the square of period was proportional to the length. So, well, what did I do with the easy one? Why don't we do period versus angle? So, how did it look? Well, you did a data table, and you'd say, okay, here's the angle, and then you measured the period, and you got a bunch of numbers. And then you graphed it. It's another way of showing the data. So when you graphed it, you put the independent one down here. So that was the one that we got to choose, which was the angle, and here you put the period. And most of your lines most of your data formed a horizontal line. And then we can make an equation from that model. And really what we do is we take some variation of mx plus b, and if it's already a straight line, then we just say, okay, what's the equation for that straight line? The y, we change the letter, and we say, okay, so what's the best letter we should use for period? Instead of saying y, we're going to say p equals. In this case, if it's a horizontal line, then the m would be equal to 0, so then actually this would disappear altogether because 0 times whatever the x value would disappear, and the b is the y-intercept. So it would be whatever value you got. Say, I don't know, 2.6 seconds, I seem to recall we had one. So there would be a mathematical way. So far, we've described all these three things in different ways. And the last one, qualitative, which just means words. There's quantitative, which means numbers, and qualitative is words. We could say there's no relationship between period and angle. In other words, if you change the angle, the period still stays the same. How to go from the graphical to mathematical model. So it's something I'm going to be asking you to do in your assessments. So the first thing is to graph that raw data. So here's an example. Someone collected time versus mass. So as the time went by, it looks like mass dumped versus time. It might be, I don't know, maybe a dump truck. Here's my really bad drawing of a dump truck that's dumping sand as the time goes by. So as the time goes by, it dumps more and more sand, so maybe that's what it is. So we look at this and we ask ourselves, first of all, is that a straight line? So it looks to me like it's got a little bit of a curve, and what kind of curve could it be? We compare it to these known graphs. It seems to me that that curve looks closest to this one here. And so how would we straighten it? We'd say, well, and now let's just take a look at these graphs and just remind us what this looks like. This one is a no relationship. This one is a sort of a sideways parabola. This is maybe an upwards parabola. This is inverse, and this is linear. It's a straight line, or we could say direct. So in this one, the formula would be y is equal to whatever that constant was. This one, if we were to straighten it out, we would say that this one is y squared is proportional to x, or we could say y squared is equal to some constant times x. On this parabola, we could say y is proportional to x squared, so it's kind of the other way around, or we could say y is equal to kx squared. For inverse, we could say y is proportional to the reciprocal of x, and there's a couple ways we could write it. I kind of like this way, we put k over x. And the linear is like we don't have to do with much at all. We could say y is proportional to x, and y is equal to kx. All right, so these are all different kind of ways of talking about this. So in this example, I think it looks closest to that sideways parabola. And so instead of graphing y versus x, now we graph y squared versus x. So that would be the next step. And so that's why on the next page here, instead of graphing mass, now they did mass squared over time. And so how do we know which relationship fits best? Well, if you look at our first one, you might say, oh, it looks fairly straight. You know, if you draw the line of best fit, they didn't do one. It looks fairly straight. If you look at the second one, you'd go, wow, actually all those dots fit perfectly on the line. So how do you know when one relationship is better than the other? Well, the first one is, you could say, is the correlation. And in this example, this is a perfect correlation. Correlation is 1. So you know the correlation is good if the correlation is close to 1. If the line's going uphill, whether it's close to positive 1. If it's going negative, whether it's close to negative 1. So I could say close to plus or minus negative 1. The second one, and I didn't put it in this sheet, but the RMSE, the closer it is to 0. Okay, is the better. In this case, this RMSE is 2.928, and if it's less than 5% of the median or midpoint of my y values, what's the midpoint of the y values? About 3,000. So 5% of 3,000 is the same thing as 0.05 times 3,000, which is what, I think 150. And the RMSE is definitely less than 150. It's like 2.928. So that's a pretty low value. The other one, and I'm not sure if I ever mentioned this in class or not, there's something in science that we call Occam's razor. Occam's says if you've got more than one answer or interpretation, take the simplest one. Simplest solution is usually better. So I'll just back up and say these relationships here are the ones that we're starting with. These aren't all the relationships there are in math and science. There are more complicated ones, and we eventually will get to some of the more complicated ones. If you have to get some really crazy, and if you say, oh, how about like y cubed versus x to the 5th power, and then it's pretty close. If you have to get some really crazy relationship that is slightly better in correlation than, say, just y and x, then sometimes it might be better to go with the simpler solution, and that's Occam's razor. Note, both graphs are correct, but have different uses. And what I mean by that, our first one, that was just mass versus time, that had this curve, and then we said mass squared versus time, in which it was a straight line. Both are correct. They both show the same data, and they both show that, hey, this looks like a sideways parabola. This one is good if you want to say, hey, as time increases, mass increases, but not as quickly. This one is great because the slope of this line is k, and so it's really good to find the formula for this because you got the slope and you can figure out the answer for that. So the last step, is to make that equation. So let's take that equation, and normally we would say y equals mx plus b. In this last one, it's not y, it's mass squared. So I would say mass squared is equal to, Now the slope, here is the slope, 949.2 kilograms squared over seconds. A little bit complicated, but we can write that in there. 949, I'll just leave it at that, kilograms squared over seconds. I'm going to put that in parentheses just so that it doesn't clutter up. And then the x is time, so I'll put t for time. And then the y-intercept, let's look at the y-intercept. The y-intercept is 0.86, and again, we're going to use that 5% of 300. That is way less than 150, so it's close enough to 0. I'm going to say, oh, I think it's probably just there because of error, so I'm just going to leave that blank. So here's my equation. Okay. What's cool about the equation is now you can solve stuff. You can say, well, after 10 seconds, how much, what would the mass be? You can, if you've got time, you can figure out the mass, or if you've got mass, you can figure out time. So you can do stuff with it. Some other things that graphs can tell you. So here's a graph. Let's look at it. It's a graph of the cost in dollars, if you're going to order, and so that would be in dollars, and music in compact discs. Oh, you guys might be too young to know, but compact discs is before MP3s were everywhere. That's how you would order music. In this case, I think it's the price if you're going to order something, let's say on Amazon. Okay, ordering. I'll write it out here. Let's say that's that this chart is from. The cost to order CDs on Amazon. So in other words, so it seems to me if you order 2 of them, it's a little bit less than $20. If you order 4, it's around $30. Okay, so there's a few things that any graph will tell you that you can look at. One is y-intercept. So in this case, the y-intercept is 3.6, and I get this from this title here. 3.6, and it would be $3.6. What would that mean? If you order 0 CDs, why would it be $3.6? Well, maybe in this case, and we have to think about it and interpret it, maybe that's the shipping cost. So that is independent of the number shipping cost of any order. Maybe they just say, hey, it costs you $3.60 no matter how many CDs you're going to order. The slope in this case is 7. Now what would the units be? It's rise over run, so it would be dollars over compact disc, so it would be dollars. So for one CD, for every one CD, it would cost $7. So that would be price per CD. Okay, one CD costs $7. Also, what is often useful to look at, I'll sort of recreate this graph, is the area under the graph. So in this case, I would talk about this area here. In this chart, in this graph, it doesn't really mean anything, because if we think about the units, this area would be what, dollars times CDs, and dollars times CDs doesn't really mean anything too much. So sometimes it means something, sometimes it doesn't. Not meaningful on this graph. Later on in our course, there we will have lots of graphs where area is important. We can use the graph now to make our mathematical model, our math equation out of this. Instead of y, this would be cost in dollars, so maybe I'll say C. The slope, we said, was $7 per CD. X was the number of CDs. Oh no, now I put C for cost. How about I use D for discs, maybe something like that. Plus, the y-intercept was $3.60 to start off with. So now I could do calculations. That could be how much would 10 CDs cost? I could solve that kind of question. And so I would say that 10 CDs means that D is going to be equal to 10. Plug in my numbers, and I get my answer. I could also say if I had $100 to spend, what's the most number of CDs I could buy, and so on. We also spent some time about proportional thinking. So once again, I'll just write out the proportions here. This one is, there's no relationship. Here I could say y squared is proportional to x. Here I can say y is proportional to x squared. y is proportional to 1 over x, and y is proportional to x. So, for example, the relationship between mass and period was no relationship. If I double the mass, the period stays the same. If position is proportional to the square of time, okay, in other words, it would look like that. On a graph, how would that look? It would look like this, right? Or if I graphed position versus time squared, it would be a straight line. What happens to p when time is tripled? In other words, if I multiply this times 3, well, what's going to happen is this is going to get multiplied by 3 squared. In other words, it's going to get multiplied by 9 would be my answer. That the position would be multiplied by 9. Energy is inversely proportional to radius, this question says. So if energy is proportional to 1 over r, and again, I could show this in a couple ways. I can say, well, if I did E versus R, it would look like this. Or if I graphed E versus 1 over R, then I would get this kind of straight line. What happens when R is halved? If I multiply this times 1/2, well, in the inverse proportional, whatever one gets multiplied by, the other one gets multiplied by the reciprocal. So what is the reciprocal of a half? The reciprocal of a half is times 2, or times 2 over 1. So what you do is you sort of flip the numerator and the denominator of the fraction. Okay, so that was a quick whirlwind tour. Is that the rest of it? Yeah, I think that's it. So hopefully that will help you, and I will see you in class.